Today's video is on chords and arcs. So first we'll define what a chord is. A chord of a circle is a segment whose endpoints are on the circle. Now it is important to understand that a chord is not a diameter. It is formed by 2 points that are on the circle, but when you connect those 2 points, it is not a diameter. It is a separate line. Okay? It does have a relationship to the center of the circle because the points can form a radius. So, how are they related? How is line segment GE and arc GE related? Well, they have the same endpoints. And the segment and the minor arc are related. Okay, they're associated with the same central angle. Notice that I drew the radii, and this central angle C would be the arc formed by chord GE. So they're associated with the same central angle. Okay, so what that means is if this central angle is 35 degrees, the arc formed by GE is also 35 degrees. Now, congruent circles are circles that have congruent radii. Remember, radii is the plural for radius. And all circles are similar. Okay? So all circles are in proportion to one another. Okay? There are no angles, so they can't be different. Now, congruent arcs are arcs that have the same measure and are in the same circle, or congruent circles. Why isn't it enough to say that congruent arcs have the same measure? Well, you could have arcs with the same measure but different lengths. And vice versa. Okay? So let's look at some examples. Are arc AB and arc CD congruent? Well, arc AB here is 40 degrees because the central angle is 40 degrees. This arc here, CD, is 38, so that's obviously no. Okay? For number 2, arc AB is here, and arc CD is there. Notice that these are vertical angles. So these 2 angles are congruent, the central angles, so that is a yes. Now, arc CD is this smaller circle. Arc AB is the larger circle. The lengths of CD and AB are going to be different. So therefore it's no, different lengths. And we'll talk about finding the lengths of arcs later on. Number 4. Well, CD, again, is this arc here, and AB is a smaller circle. So we don't know exactly what the relationship of the radii are, but this is no because it could be different lengths. So now we have some rules to worry about as well. Congruent central angles, arcs, and chords. So the first theorem is, within a circle or in congruent circles, congruent central angles have the same arcs. The converse of that is also true. Within a circle or in congruent circles, congruent arcs have congruent central angles. So in my drawing here, these two angles are congruent. Therefore, arc AB and arc CD are also congruent. Okay, the converse of that is also true. If the two arcs are congruent, then angle AOB and angle COD are congruent. Okay, the next theorem, within a circle or in congruent circles, congruent central angles have congruent chords. The converse of that is also true. So, these two angles are congruent. Therefore, these two chords are congruent. So if the central angles are congruent, then line segment AB, or chord AB in this case, is going to be congruent to chord CD. The converse of that is also true. If the two chords that are formed are congruent, then the central angles will also be congruent. So basically, the angles create the chords. Within a circle or in congruent circles, congruent chords have congruent arcs. Okay, and converse of that is also true. So if these two chords are congruent, these two arcs are also congruent. And the converse of that is true. So line segment AB is congruent to line segment CD. Arc AB will be congruent to arc CD. Okay, and the converse of that turns out to be true as well. Okay, so we can solve the next problem. Here we have two chords that are congruent. Therefore, these two arcs are congruent. Congruent chords have congruent arcs. So we can set this up as 2x equals x plus 40. Solving for x, we get x equals 40. Okay, next example. These two arcs are congruent. These two chords are congruent. Therefore, these two arcs are congruent. So we set them equal to each other. 3x plus 11 equals 2x plus 48. X plus 11 equals 48. And therefore, x equals 37. The next theorem states that within a circle or in congruent circles, chords equidistant from the center, or centers, are also congruent. So here we have EG, line segment EG, and line segment EF. They are perpendicular to the chords. If these two segments are congruent, and what we're going to have is the form of right triangles. If EG equals EF, then the two chords are congruent. Okay, and the reverse of that is true. If the two chords are congruent, then those two line segments are congruent, and we form right triangles. So we could probably use the Pythagorean theorem to find out the length of these chords, because we end up with congruent triangles. Okay, so for example, okay, we have that these two segments are congruent. Okay, since they're equal distance to the center, the chords are equal distance. From the center, chords are congruent. Okay, so AB equals CD. So I can set up x plus 9 equals 4x minus 19. 5 equals 3x minus 19. and therefore 24 equals 3x, and x equals 8. Now there's actually another item about chords and diameter. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arcs. So if AB is a diameter of, and line segment AB is perpendicular to CD, what happens is that these two segments get bisected. So CE is congruent to ED, and CA, the arcs, because now these two segments are congruent, is congruent to arc AB. In a circle, if a diameter bisects a chord that is not a diameter, then it's perpendicular to the chord. So if line segment AB is a diameter and line segment C is perpendicular to ED, so we have perpendicular lines, then what happens is these two segments are congruent. So AB is perpendicular to CD. Again, forming right triangles. We're going to go back to using the Pythagorean theorem to find chord lengths, diameters, radii using the Pythagorean theorem. In a circle, the perpendicular bisector of a chord contains the center of the circle. Line segment AB is the perpendicular bisector of chord CD. Therefore, line segment AB has to be a diameter. So AB contains the center of the circle and AB is the diameter. So it contains that circle, and we'll call it O for the sake of this. So let's go through some examples quickly. So, if OA is perpendicular to GT, and GT is 16, so this entire length is 16, well, that means it bisects it. Therefore, GX is going to be 8. The arc GT is, the entire thing is 80 degrees. So because it bisects, this is going to be 40. And this is going to be 40. The measure of arc GA is 40 degrees. The measure of arc G DT, which is everything else, will be 360 minus 80, or 280 degrees. Remember direction when you name arcs. Okay, here we have AB is 12, so this length is 12, it's perpendicular, so this is going to be 6, this is going to be 6. Okay, this means they're equal distance to each other, so these are congruent. Okay, so we can set this up as 7 squared. We're trying to find x. This is 7. The radius is 7. This will be 6 and 6 here. So 7 squared equals x squared plus 6 squared. Okay, so 49 equals x squared plus 36. 13 equals x squared, so x equals the square root of 13. And that's perfectly acceptable for what CG equals. And finally, okay, according to the given, this is 20, this will be 20. Okay, CD is 25, and we're trying to find out if that is true. So we're going to use Pythagorean theorem to see if we have a right triangle. So 25 squared equals 20 squared plus x squared. Solving for x, we get x equals 15. And therefore, it's a right triangle.